Okay, let's dive right into this explainer. Just take a second to absorb the sheer scale of a volcanic eruption. Witnessing something like this is an incredibly visceral, almost terrifying demonstration of the immense power hiding right below the surface of our seemingly quiet planet. We walk around every day treating the ground like it's this permanent, unchanging fixture, right? But events like this prove that the Earth is, well, it's very much a live, dynamic engine. And that brings us to a really fascinating question, one that totally shatters that illusion of a still, permanent planet. What actually happens when the solid, dependable ground beneath your feet suddenly decides to move, or to crumple, or literally blow wide open? To answer that, we've got to look a lot deeper than the surface. Welcome to the Explainer. Today, we're going to uncover the massive hidden engine that drives Earth's most dramatic geological changes. We're going to look at how towering mountains are actually born, why volcanoes erupt with such unbelievable fury, and what causes the ground to violently snap during an earthquake. Here's how we'll map out our journey today. First, we'll cover the restless Earth, then how tectonic plates move. After that, we'll get into the birth of mountains, check out volcanoes, Earth's fiery vents, and wrap up with earthquakes, the violent snap. Let's kick things off with Section 1, the restless Earth, a planet in motion. So the world's tectonic plates fit together exactly like massive puzzle pieces, and the places where they meet are called plate boundaries. Because these plates are literally always moving, these boundaries are massive hotspots for geological change. Notice that thick band circling the Pacific Ocean? Yeah. That's the famous Pacific Ring of Fire. It marks the exact plate boundaries where sudden, violent changes, like the volcanic eruptions and earthquakes we're talking about today, most frequently happen. Moving right along to Section 2, how tectonic plates move, the gears of the engine. Okay, so the absolutely crucial point here is that tectonic plates interact in three very specific, distinct ways. They can move together, they can move apart, or they can slide past one another. Each of these distinct movements acts like a totally different kind of gear, driving a completely different, dramatic outcome up on the surface. Now, when plates move together, one massive plate will often literally slide underneath the other in a process we call subduction. The rock from the bottom plate gets forced deep, deep down into the Earth's fiery mantle, where it actually melts and becomes part of the mantle itself. It's basically a massive recycling program, but on a planetary scale. On the flip side, when plates drift apart, they break and crack. They get thin enough to let liquid rock from the mantle erupt upwards, cool down, and form brand new crust, which, by the way, is the birthplace of a volcano. Alternatively, when plates slide past each other, there's just a tremendous amount of friction. Because these are unimaginably massive, heavy slabs of rock, they don't just, glide smoothly. They stick. Over the years, pressure builds and builds until the rock just can't hold it anymore. And eventually, the pressure causes a violent movement. That sudden release, that's an earthquake. If you want a fun, relatable way to picture all this heavy physics without needing a full-blown laboratory, just imagine holding two soft-centered chocolate bars and slowly pushing them together. Just like the solid chocolate shell would crack and the soft center would ooze or fold upward, the Earth's crust crumples in the exact same way when these massive plates collide. It's a really great mental model for the unbelievable forces at play here. Plus, chocolate. Which brings us beautifully to Section 3, the birth of mountains, a slow-motion collision. When plates move together but don't subduct right away, all that immense pressure has to go somewhere, right? So it causes the rock layers to literally crumple and fold upwards. The compression from that tectonic movement forces those flat layers into distinct, wavy folds, creating what we aptly call fold mountains. And a truly fascinating detail here is that this immense folding doesn't just happen on land. These massive mountain ranges can form right at the bottom of the ocean, too. Crazy, right? Now, take a look at the mind-boggling scale of time we're dealing with here. When geologists talk about new mountains, they mean ranges like the Himalayas in Asia or the Rocky Mountains in North America. And those took anywhere from 10 to 25 million years to form. In geology, that's considered a quick process. By contrast, the oldest fold mountains, like the Ural Mountains in Russia, were formed over 200 million years ago. These peaks are the result of unimaginably slow, relentless pressure. Let's shift gears from millions of years of slow growth to Section 4, volcanoes, Earth's fiery vents. Before we go any further, let's clear up a classic debate right off the bat. You probably hear these two words used interchangeably all the time, but there is a strict scientific rule. It's called magma when the liquid rock is trapped safely underground. but the exact second it breaches the Earth's surface and erupts into the open air, boom, it's called lava. Same exact fundamental material, completely different location. Deep inside a volcano, magma from the mantle rises up through cracks, traveling through a main central vent. Once it's at the surface, it erupts as lava and forms these massive ash clouds. As these materials settle, cool, and harden, they actually form brand new rock. What this means is that every single time a volcano erupts, it deposits a new layer, literally making the volcano bigger and bigger with each and every explosion. It builds itself. So, what actually triggers those violent eruptions? Well, the anatomy of a disaster goes step by step. First, really thick magma builds up immense pressure deep underground. Second, gases that are dissolved within that magma begin to expand, desperately seeking a way out. Third, this intense culmination of pressure and expanding gas results in a violent eruption that shoots rock and ash high into the atmosphere. And fourth, the surrounding environment reacts. These violent eruptions can cause avalanches, or if the volcano happens to be near the sea, the sheer force of part of the mountain blowing off can trigger absolutely devastating tsunamis. Because of these massive risks, we actually categorize these giants by their threat level. An active volcano is exactly what it sounds like. It's erupting right now or could erupt at literally any time. A dormant or inactive volcano is essentially just sleeping. It hasn't erupted in a really long time, but the underlying plumbing is still intact. And finally, an extinct volcano has been cut off from its magma supply entirely. It's never going to erupt again.
Finally, we reach our last section, Section 5, Earthquakes, the violent snap.
The consequences of earthquakes are immediate and utterly devastating. Remember those plates sliding past each other that we talked about earlier? When the friction finally gives way and those stuck plates aggressively snap past each other, the violent movement sends massive shockwaves straight up to the surface. It can completely destroy heavy infrastructure like paved roads, buckle skyscrapers, and alter entire landscapes in an instant. The sheer level of destruction we're talking about is measured by something called earthquake magnitude. The magnitude, or overall strength and size of the quake, depends entirely on two major factors: the size of the fault at the plate boundary and just how far the rocks actually move when they finally break free. And get this, in the largest earthquakes, those massive slabs of rock can move tens of meters in a matter of mere seconds. The amount of energy released is honestly incomprehensible. So, to wrap up our explainer today, I want you to remember the staggering contrast of our restless planet. We live on a world of wild extremes. The exact same tectonic forces that require 25 to 200 million years to slowly, patiently push rock upward to build majestic mountains can also tear the ground apart in just a few terrifying seconds during an earthquake. I'll leave you with this final thought to ponder. Knowing everything we've covered today, the moving puzzle pieces, the subduction zones, the fiery volcanic vents, and the snapping faults, the next time you stand outside, take a look at the seemingly still ground. Ask yourself, what immense, invisible forces are slowly building up right beneath your feet? Thanks for joining me on this explainer, and keep questioning the world around you. Okay.